Hello everybody and welcome to the online certification course on cryogenic electronics for quantum computing. This is lecture 13 and we will be doing this lecture concentrating on the second order effects in bulk MOSFETs when you reduce the channel dimensions. So, what second order effects we will learn is basically the body effect, right? We will learn the concept of body effect, and then how does the body voltage affect the threshold voltage, and the problem with respect to threshold voltage. And of course, as you can understand, we will show you that body effect is basically undesirable because your threshold voltage starts to shift with respect to the body bias. So, we will explain the physics behind it. Now, before we go ahead and do the second order effect, which out of which the first one is a body effect, I need to say what is the second order effect. So, typically when the device dimensions are large, which means the channel lengths are large, the electric field typically is not very large along the transverse direction, right. So, there are two directions which you need to work out. One is the electric field from source to drain, another is from gate to the bulk. So, there are two electric fields. Whenever you do a long channel, whenever you have a very long channel, you do not care too much about the electric field along the y direction, and you say that it is only dependent on x. However, as you reduce the dimension of the device, you go on seeing that both electric fields becomes prominent because you will be scaling it in all the dimensions, and therefore you will always have these second order effects coming into it. So, second order effects which you see are primarily because of shortening of the channel lengths, right. We are reducing the channel length, shortening the channel length, or reducing channel length. So, when we are reducing this channel length, we have these phenomena coming into picture in a much more drastic manner. So, first one is basically your body effect. So, these second order effects we will study in the subsequent lectures. One is drain induced barrier lowering, we will have a look. We will also have a look at velocity saturation, carrier velocity saturation, and then finally we will do CLM, channel length modulation. Maybe not of the same order, but nonetheless these second order effects are important as far as the MOS bulk device are concerned. First of all, what does the first one tells you? I will just give you a small brief insight rather than going into details of it. It is drain induced barrier lowering. What does it mean is that as you start reducing the dimension of the device or the channel length of the device, you are effectively bringing the drain closer to the source, right. And therefore, drain starts to have a larger impact on the profile as compared to the gate, because now drain is coming closer. Now, please understand what happens is that there is a depletion region in the source side, right. Basically, if you look at your bulk MOSFET dimensions, there is a depletion region on the source side, right. And let us suppose this is drain and I apply a drain bias which is say positive in dimensions. So, applying a positive drain voltage here. So, there will be also a, let us suppose my gate voltage is 0, right. My gate voltage is 0 here, and I have grounded it. My source is also, let us suppose, grounded, but still you will have, this is n plus p, n plus p. So, you will have a depletion region here. As you go on making the channel length shorter, you are trying to bring this drain closer to the source, and when you go on increasing the drain bias in a positive sense, you are actually doing what? You are trying to reverse bias this junction, this drain to substrate junction, right. And as a result, what you have seen this point, that the depletion region becomes something like this. So, it enhances the depletion region. However, when you apply a positive bias here, the electric field within the depletion region at the source end reduces, and there is the barrier drops down, the energy barrier drops down, and you do have a larger current flowing through this, which means that the threshold voltage will change as the drain voltage increases. So, as the drain voltage increases, since you are able to reduce the depletion thickness at the source end, the effective energy reduces, and therefore, with a smaller amount of gate voltage I will be able to form the channel. That is the concept of drain induced barrier lowering, right, and we will be concentrating on that later on. Let us come to the next concept, which is velocity saturation of carriers. Now, you see, if you remember very clearly in silicon, in silicon, if you plot velocity versus electric field, right, it comes something like this, right. So, as the electric field increases, the velocity first initially increases, becomes a nonlinear function of electric field, and then it becomes almost constant independent of the electric field, right. So, when you reduce the dimension of the device, the electric field in the x direction goes on increasing, and as it goes on increasing, you do have a phenomena of the carrier velocity saturating near the drain end, right, because you end up having this electric field. And why is it like this? Because as you first increase the value of the electric field, so velocity is given as mobility multiplied by electric field. So as the electric field increases, you assume that my mobility is constant, my velocity increases linearly with respect to electric field, and that is what is happening here. As you move slightly further, the electric field becomes larger, mobility is a non-linear function of electric field, and therefore velocity becomes a non-linear function of electric field in this region. After this, what has happened is that the velocity is constant, which means acceleration is 0. Why velocity is constant? Because there are two phenomena which are happening. One phenomena is by virtue of the electric field, these electrons are pulled towards the drain end. But when they are pulled towards the drain end, they also suffer from a larger scattering, larger number of scattering. So when the number of scattering and the electric field induced forward velocity become equal, the velocity becomes constant. So we have two, as I told you, we have two. One is the force along this direction, and there will be another force because of scattering in another direction. When these force becomes equal, the velocity is basically constant, acceleration is equals to 0, right. Effective force on the particle is 0 in that case. So that is known as a velocity saturation, very prevalent in all low channel or short channel devices. Let us come to the last one, channel length modulation effect. As the drain voltage goes on increasing for very short channel devices, the channel length actually starts to reduce. The effective channel length starts to reduce, which means that the current will go on increasing as you have larger and larger drain current. Let me show you. So if I plot current in a MOSFET versus VDS, this is drain current, then you will see if you do not have channel length modulation, you will have this current almost constant with respect to VDS, correct. Now if you do have a channel length modulation, then because the length reduces and we know that the current is proportional to W by L, since L reduces by a factor, so it is L minus delta L, this I will increase slightly, and that becomes a function of the voltage applied. So you will get the current to rise with respect to VDS for large values of VDS, which was ideally constant. This is known as channel length modulation effect, right. Let us come to the body effect principle here and go step by step. Now let us have this PN junction diode here, or a MOSFET here, and this is N plus region, which is basically my source grounded. I have applied a drain bias at the drain end. These black colored are metal contacts. These are metal contacts, right. These are metal contacts, and I have applied a positive gate bias, and there will be of course a channel being formed. This is the body substrate. Substrate means I will tell you why. Where is the substrate? So the dimension of the device is something like this. Then you have this, and this is your gate. So this is your gate, and this is the contact. This part is this part. I have an oxide layer, and then there will be a gate. This is N plus. So this is this and this. Here you apply VDS, and this is grounded. This is a contact here, and here you have this body VB. VB means voltage at the substrate or body, and let us assume that I apply a negative bias here. That is what I have done, negative bias here. Or let us first take the most easiest one. We give the bias VB equal to 0. If I put VB equals to 0, it effectively means that the substrate of the device is grounded. If it is grounded, then if I apply a gate bias here which is positive, the electric field will be from this direction to this direction. I hope you understand this point. Now let me give a positive bias, make it VB greater than 0. Then what will happen? This will be, let us suppose this is 5 volts, and let us suppose it was initially 0, now it is 3 volts. So the difference between the two volts will be 5 minus 3, which is 2 volts, and therefore electric field will reduce. The effective electric field in the transverse direction will reduce if your body bias starts to become larger and larger. Now if the reverse is true, if my VB body bias is less than 0, which means that negative bias has been given to the substrate of the device, the effective electric field will increase, right. Now there are two ways of looking at it. We say that my bulk voltage of the N MOSFET is below the source voltage. The source voltage is grounded, and therefore I am assuming that VB is less than 0. Now let us see what happens in this case. Now you see source and drain, as I discussed in the starting of the class, that you will have a depletion layer here, which is just because you have an N plus P layer. This is basically P substrate, right? And this is an N plus P layer which is C, and that's the reason I've shown you here as P plus. So assume this to be as a P plus substrate. P plus substrate means highly doped with third group elements. It's a P type substrate, and then what we do is we apply a positive gate bias on the gate side. If I wouldn't have applied any drain bias, then the thickness of the source depletion region and the drain depletion region will be almost the same. That is first thing. The second thing is there will be also a depletion region within the N plus region, but that will be very, very thin. Most of the depletion region will be into the semiconductor, right, which is the substrate side of it. So this is we have learned. So we have therefore learned two things. I can give positive, negative or zero bias to the substrate. If there is a bias given to the substrate, we define that to be as a body effect. And what will it do? It will change the threshold voltage of the device. What is the threshold voltage? Threshold voltage of the device was defined as that gate voltage at which a channel is formed, electron channel is formed, and it becomes as much N type here as it was initially P type. So if there were 10 to the power say 80 number of holes available there per unit volume, then that should be 10 to the power 80 number of electrons per unit volume will give you the inversion layer formation, right, and that will be defined as my threshold voltage. So the way to look at it is schematically is this is my bulk MOSFET N type, source is grounded, drain is given a voltage, gate is given a positive voltage, and I have put my bulk in a negative sense less than 0. Let us see what will happen. Case 1 is when Vs Vd is both 0. So I have grounded this, and Vg is somewhat less than threshold voltage. When you know it's somewhat less than threshold voltage, so there will be a depletion region formed just under the gate, and there will be no inversion layer, and my bias voltage is 0, as substrate bias is 0. I have applied a positive bias on the gate side, but it is not as large as threshold voltage. So if it is not large, it will simply form a depletion region at the silicon dioxide interface, and that will be given by Q depletion, Qd, right. Q depletion will be the charge. There will be no inversion layer because your Vg is not equal to the threshold voltage of the device here, and my both biases are 0. Now let us come to the second phase, that we have made my Vs equals to 0. I am grounding it. However, I am making my Vb more and more negative, right, which is basically negatively biased. And therefore, what will happen is, since you have applied a negative bias, holes will be attracted towards the substrate below, and therefore there will be larger negatively charged left behind, and therefore the depletion thickness will become wider. Please understand this point. See, what we have done is, I have still not applied a drain bias, let us suppose, but in the substrate I have applied a negative bias, and this is a P type substrate, right, and this is my source and drain. So what has happened is, initially there was depletion region. Now when you apply a negative bias, you are effectively pulling all the free holes towards the substrate, and therefore the depletion region on the silicon dioxide interface will go on increasing, will become wider. That is what is written there, which means that the number of depletion fixed charge carriers becomes more and more when Vv becomes more and more negative, of course, which means that if I go on increasing the negative value of the substrate bias, I introduce more and more depletion region near the silicon dioxide interface. So that region goes on increasingly more depleted. So let me go back to that stage and explain to you now from that angle. So if your QB is negative, you have a depletion region formed. Of course, you need to increase your gate voltage in order to invert the depletion region, and therefore what happens is the threshold voltage rises, which means that if you have applied a negative bias, right, negative bias to whom? To the substrate, then if you have applied a negative bias to the substrate, your threshold voltage will actually go on increasing, and the reverse will be true if you have applied a positive bias. I hope this conceptually it is clear, and that is the reason we come to the next stage here, and I will start from here and I will show you. So as my Vb becomes more and more negative, my depletion thickness or depletion charge increases, which effectively increases my threshold voltage, and this is known as body effect. Reverse will be true if I make my Vb larger and larger, more positive and more positive, Q depletion will fall and threshold voltage will fall. So ideally, if I want my threshold voltage to be fixed, then it is imperative that my substrate bias should also be fixed. It should not change with external bias. This will ensure that my threshold voltage is fixed. It is undesirable because you do not want the Vb to change when the device is functioning. You have a circuit made with a MOSFET. Now you want to change the threshold voltage of the device while it is working. What should you do? Just give a substrate bias and your threshold voltage will change. Right? Just to inform that particular see the equation which is shown in this slide. The threshold voltage is given as phi ms, the difference between the metal semiconductor work function, plus 2 phi f. Remember 2 phi f was what? 2 phi f was basically the Fermi potential. You require 2 phi f because one to deplete and one to become n-type inverted. We have already discussed that point. And the last point is critical for this from this point of view of body effect. It is Q depletion by Cox. Now, the very fact that Q depletion is increasing will make my VTH go higher and higher. This is known as the body effect, and this has got an adverse impact on the performance of the device if you don't want the threshold voltage to change. Right? Okay. So, this is the basic idea or the effect of body effect. Now, I will not go into details how the expression was derived, but let me show you how it is done. So, this is given as VTH is equal to VTH 0. VTH 0 is the threshold voltage with 0 substrate bias. See, if I would have given a 0 substrate bias, then the threshold voltage will be given as 0, right? So, VTH 0 is that threshold voltage when VSB equals to 0 or source to bulk is 0. This is 0. So, this plus gamma times 2 times phi f plus VSB minus root of 2 phi f. Assuming that 2 phi f is almost constant, it is not varying with any factor. What you see interestingly, as this value goes on increasing, right? The value, this quantity goes on increasing, and therefore the threshold voltage goes on increasing, and this is what I was telling you. This is source to bulk, right? Source to bulk. So, source is grounded. Now, if source to bulk or body, either of the two. So, VSB, when we say VSB, this one is source and this one is either defined as bulk or a body, and source is generally grounded. So, source is grounded. Vs is equals to 0. How do you define VSB? It is Vs minus Vb, correct? And that is the reason you will see that there will be always a change the value of VSB. Now, let us suppose your bulk was kept at a positive voltage, then Vs is 0. So, 0 minus a positive voltage will be always a negative voltage. So, what you will get? You will get a negative here, right? So, as the value of VSB goes on increasing, this negative factor becomes larger and larger and threshold voltage drops down. This we just now learned, right? So, we were able to therefore correlate the mathematics, the formula with the physical factor. If bulk is negative, then VSB will be positive, right? Because this will be Vs minus Vb and this will be Vs minus of minus Vb, and that will be equals to Vs plus Vb. So, in the negative sense, if you go on increasing, VSB will increase and VTH will increase, and that is what we learned in our previous turn. You see this part, right? So that is the reason we will say that we can change the value of the threshold voltage by simply changing the value of VSB. This gamma is defined as the body effect coefficient, gamma. This is known as, yes, this is the body effect coefficient, gamma, and it depends upon the substrate, your concentration of the charge carriers in substrate, and it also depends upon Cox, right? Let us see what happens. If I take the value of Cox to be small, let us see what will happen. If I take Cox to be small as compared to a standard benchmark case, gamma will be larger. Gamma will be larger, implying that the weight associated with the second part of the equation will be larger, which means that for a smaller thickness, the rate of change of the source to bulk will be much larger in the threshold voltage as compared to a larger thickness, which means as the device dimensions are reduced, oxide thickness will reduce. When oxide thickness reduces, your Cox will increase. Cox will increase means gamma will go on decreasing, right? So, what is Cox? Cox, if you remember correctly, Cox is equals to epsilon ox by Tox. So, as you lower the dimension of the device, Tox also scales down, which means that Cox also increases, which means that gamma actually decreases. As the gamma value decreases, threshold voltage becomes a weak function of VSB, right? And that is the reason you get some variations in the value of the threshold voltage with varying values of VSB. Okay. Let us look at the problem on the effect of VSB on threshold voltage, and this is a simple problem which we did. So, you need to plot drain current. So, this is my problem. So, this is I have a MOS device, enhancement mode MOS device, where the substrate bias is shown as Vx. You have applied a plus 2 volt on the drain side and a plus 1.2 volt on the gate side, because of which a drain current is flowing. Now, if Vx is sufficiently negative, the threshold voltage of M1 will exceed 1.2 volt and the device will be off. You remember what was the concept? The concept was that for the device to be on, gate to source voltage should always exceed the threshold voltage of the device. What is my gate voltage here? Plus 1.2. What is the source voltage? Is grounded. So gate to source is 1.2. However, if you apply a positive bias here on the Vx, the effective gate voltage will reduce. You get my point? So for example, if my Vx is say exactly equals to 1.2 volts, then the effective electric field in the transverse direction is 0. So you don't have any effective field. Whereas if this would have been 0, the effective gate voltage will be 1.2. If this is plus 1.2, then there will be no electric field available. On the other hand, if this would have been minus 1.2, there would have been a field equivalent to 2.4 volts on the gate side, which means that the threshold voltage is a function of the value of Vx I have shown you there. Now, we have assumed that the question gives you that the gamma is this much, Vth0 is 0.3 volts, and we assume that 2 phi f is 0.7. Coming back to the previous expression, we say that V is equals to Vth0 plus gamma times root phi f plus Vfb minus root of 2 phi f. This is known to me, this is known to me, this is also known to me, this is also known to me. I can predict the value of H, right? So what the question is, since Vx is a variable, I tell this to be this if you remember, this is gamma Vth0 is 0.3. Then you have gamma is how much? 0.4 and 2 phi f is 0.7. So 2 pi f minus Vx1 minus 2 phi f is equals to 1.2 volt. This is the Vth, right? So hence, if you solve this above equation, you will get Vx to be equals to minus 8.83 volts. And therefore, if Vx is between 0 and 8.83 volts approximately, I will increase according to the relationship here. You remember when we were discussing earlier in the previous case, we said that my VDS of a device should be greater than equals to VGS minus VTH for the device to be in the saturation. And in saturation, what we told? We were told that the effective current should be equals to some value into VGS minus VTH whole square. Now what we did is, interestingly, I took VGS here, and in place of minus VTH, we put this formula. This formula is coming from where? This. So you simply go on varying the value of Vx and you will get the plot of ID, right? So this is a straightforward way to check how the current changes with respect to body effect, right? I hope you understand this, how we did it, because I am assuming this is saturation. Saturation means the drain to source voltage is much larger as compared to VGS minus VTH, right? Now this is 2 volts, so this is plus 2 and this is 0. So this is quite large between drain to source. So I am assuming that the device M1 is in saturation. If it is in saturation, my current is proportional to VGS minus VTH whole square. But my VTH now becomes a function of Vx, which is x1, which is basically the body or the bulk potential, and therefore what I do, I plug that equation and place it exactly at this point where so my VGS minus VTH, I place it this particular point at this particular point, and it becomes a function of Vx. All other functions are known. This is known, 2 phi f is known, gamma is known, V0 is known, fixed value of VGS is known, W by L ratio, Cox, mu and everything is known. Therefore, I becomes a function of Vx. Correct? And that is quite interesting phenomena which we see. So if you plot, therefore, I get such type of expression, which means that if you plot Vx with respect to ID, you see the current, which means that when Vx reaches to approximately equals to Vx1, the current will be 0. It will go into cutoff. And as the voltage, substrate voltage goes on increasing, the current goes on increasing, becoming maximum, and Vx equals to 0. We have already seen that. We have not, so understand, Vx is not move ahead of 0. But even if I move it, so when you put Vx equals to 0, what you will get is Vx equals to 0 means this, so this becomes 0, this gets cancelled out, and therefore this quantity goes to 0, the second part of the quantity goes to 0. You are left with Vgs minus V0, right? Vth0 is 0.3 already available to you, Vgs is known to you, you can get the value of ID, and that is the maximum ID which you are getting in this case. Correct? So this is how the body effect applies to this thing, which means that this is a methodology by which, though undesirable if I want the threshold voltage to be fixed, but this is one of the methodologies by which we can actually predict a priori how much current needs to flow. So if I want to change the current while the device is functioning, this is one of the methodologies by which you can do it technically, right? As I told to you, body effect is usually undesirable, but let's see what will happen? Now let make a circuit which is shown here. Let us assume this to be as a simple input here. So when this input is less than the threshold voltage of M1, this will be cut off and V out will be just given by this formula, and so on and so forth. Now let's first do case study and say that we are ignoring the body effect, which means that my substrate is grounded. If the substrate is grounded, then I know the current flowing through the device is given by 1 by 2 mu C oxide W by L V in, which is the gate voltage, minus V out. V out is this one. Why? Because V in minus V out is nothing but VGS. So this function is basically VGS minus V square. So current is I1. So therefore, if V in increases linearly, I will automatically get the output voltage will also increase linearly, and they will be parallel to each other because V equals to IR, right? And therefore, simply current will be increasing linearly. If I increase the value of V in, or the current will increase, and this current into multiplied by resistance will give you the output voltage, and the output voltage will also increase, right? This is the case one, where we are ignoring the body effect. Let's see if we don't ignore the body effect, what happens. Now in this case, we are saying that let's not ignore the body effect, and there might be some finite value of potential, be it positive or negative, at the body of it. Now we try to go on increasing the value of V in. As we go on increasing the value of V in, V out will surely increase. There is no problem on that. But as the V in value becomes larger and larger, we have just now seen that the threshold voltage starts to change. Because of the changed threshold voltage, the effective current flowing through M1 will change, and therefore V out will change. You got the idea? See, so that is written here in this slide, that as V in and hence V out becomes more and more positive, the potential difference between the source and the bulk increases. Why? So because source is connected to V out. So what will happen? This will go on increasing, means source to bulk value will go on increasing. And as it increases, it raises the value of VH. As it raises the value of VTH, what happens? The current starts to fall down, and that's the reason your V out starts to change, right? So the equation for the current I1 implies that V in minus V out, which is VGS, must increase so as to maintain the current constant. Why? Because your threshold voltage is rising. Please understand. Since your threshold voltage is rising because your V out is increasing and your VBS is increasing, to maintain the same current, your gate to source voltage should increase, which means that the difference between V in and V out should be larger and larger. And that is what is happening as you make the more in time. So you see, it is getting stretched out, which means the difference is becoming larger for the same current to flow. So therefore, you understand, it's sort of undesirable in places where you don't want it. In certain places, it is desirable. So let me recapitulate what we learned today for this lecture. We primarily concentrated this thing on body effect, right? And we saw how body effect actually influences the threshold voltage. And then we also saw the equation for body effect threshold voltage change, body effect VTH expression we saw. And how is it VTH is a function of VSB? That's what we saw. And then we took a circuit as an example, and we try to show how does the influence of the substrate bias changes the value, right? So with this, we stop here for this lecture, and we will take up the other second order effects in the subsequent lectures. I hope you enjoyed the lectures. Thank you.